Let's keep it moving. Next up, we are talking about how privacy simply scales for better. Our friends from Polygon are going to take it from here. Thank you very much.
Cool, thanks a lot. And yeah, today I present to you Polygon Mining. It works quite similar to Aztec, and I would say what combines these two ideas is it levels up the blockchain design a little bit, because it leverages the zero knowledge property of zero knowledge proofs in the core protocol, and this scales way better and provides privacy at the core protocol. But the simple idea is, if users prove their own state transition to the network, there's way less burden on the network itself. And if users also store their own state, then the network can stay very small and doesn't need to recompute everything. So, but the design of such a blockchain must be a bit different. Also, when you want to have expressive smart contracts, but I will just walk you through. So, but yeah, the first question: do you know how many TPS cache in the European Union has, roughly? What do you think? How many transactions per second?
10K.
Pardon me?
10K.
Yeah. Yeah.
Maybe more than that.
Maybe more than that. Yeah. We don't know because it's private. No one tracks it. So yeah, which actually helps us. We don't track every transaction. Blockchains normally track every transaction, which, like I say, limits the scalability. But we know it scales quite nicely. I've never met someone who says, I cannot give you this 10 euros because there's a congestion in the real world. Roughly, there is an estimate of 20k TPS, so we are quite good. But let's keep that in mind. Well, the easy story here is that blockchains don't scale because they verify by recomputation, right? That means all transactions need to be transparent, and they need to be re-executed or recomputed by the network. So the block producer executes all transactions in a block, and then he proposes a new block to the network, and all the other nodes re-execute to the state, to their local state, re-execute that transaction. And this doesn't scale, basically. We know that already, and still, lots of our blockchains that are used today work in this principle, because it helps us to keep this promise of don't trust, verify. I forgot, should I talk in English or German actually? Well, okay, that's good. So, but basically we want to keep this promise, don't trust, verify. So, and the core tool to do that is transparency normally. So we basically can re-execute everything because everything in the blockchain is transparent. So we actually need something, if you want to overcome this, that is verifiable but not transparent. And this, at its core, is actually a zero-knowledge proof. This is exactly what it is. So the prover proves to the verifier something, and the verifier knows it's correct without getting more information than the statement itself. So this is exactly the truth. So we need something that you can verify a statement or a computation, but it's not transparent. So zero-knowledge proofs will help us to scale blockchains in a different way than most ZK EVMs or zero-knowledge products work today. But in mining, you can simply think that users prove what they do. So we have this guy here. He said, I did something. Here's the proof. And all the other people can say, okay, that's correct. Because he uses a zero-knowledge proof, right? And so zero-knowledge proofs or client-side proofs, like on my local machine, I create a proof of my own state transition, send it to the network. This obviously gives me privacy. Some even say that this is the only way to real privacy, because all other solutions, if I encrypt something afterwards on the blockchain, or if I use FHE, then I have the encrypted state in the blockchain, and eventually, maybe even after years, someone can decrypt it. So the only real known way to privacy is a zero-knowledge proof. Like the data never leaves my computer. I just send a proof, people can verify it, they know it's correct, but no one knows what I did. And our thesis is it also gives you way better throughput probability, way better throughput properties for your blockchain. That is because if the blockchain doesn't need to re-execute every transaction, they just verify proofs, and in the sense of Starks, how we use it, the complexity grows logarithmically. So verifying a proof will stay cheap even if you prove a complex program or a complex execution. That gives you actually way better throughput. I will show you how. Even though, like in our system, you can do client-side proofs, but there's also like network proving for network transactions. But the more people that use it privately, the better the network scales. So privacy in mining is the cheaper option. And this is a paradigm shift, because normally on a blockchain, if you want to do something private, it's super expensive and highly complicated, because we add privacy afterwards to a protocol that is inherently transparent. So we need to hide information, or we need to encrypt something. And if there's privacy at the protocol level with user zero-knowledge proofs, it's the cheaper option. So the technical architecture of mining must be different to provide these features. But basically, it's a zero-knowledge rollup. So some users send transaction data, clear data to the operators. Some just send the proof, and the operators, they verify that or create the proof for network transactions, and the state diff goes to Ethereum itself. So I know this is a questionable statement, but we say that the security is inherited from Ethereum then, because we settle there. It's a separate chain with its own consensus mechanism with a permissionless set of operators. And it's non-EVM, because the EVM, for the Ethereum virtual machine, inherently has this transparency rule because they keep all the state in their trees, and as I said before, we need to apply the state with every transaction. So a transaction in mining is different, but it's inspired by the actor model. And probably you know the actor, who knows the actor model from databases, or this is what scales data somehow. Like actors, you can think about them as state machines with inboxes, right? So every one of you could be its own state machine, responsible for its own state. And you have an inbox, so you get messages, and then you can change your state, and as a result of that, you can send out new messages to other actors. So you have asynchronicity in the network, right? So you don't need a sequencer, basically, that organizes that flow, but these actors can send messages to each other to trigger state changes. And this is like a way more resilient way of big databases that have high throughput. And they communicate via message passing, and this asynchronicity is important because this is how we get parallel transaction execution, basically. And this is why it scales better. But in mining, we have accounts and nodes. This is how we interpret the actor model. And the accounts are our actors, and the nodes are their messages. So we combine Ethereum's account model, and it is pretty similar. So we have accounts, and they are stored in a database. And these accounts, they can hold assets, and they have code, like an interface, or you can interact with the account. They have some storage and the nodes, and then there are nodes, like in Bitcoin in the UTXO model. So we have an account and UTXO model combined, basically. And these nodes, they can also hold assets and have a little script. When you consume a node into your account, then you need to execute the script. So, and this is how it works on a high level. These accounts send nodes to each other in an asynchronous way. And obviously it's a bit more complex, but this is a mental model. So how does it look like? So I always say, like, when you understand how a transaction works in mining, then you will understand the protocol. So let's see. But let's recap how a transaction works in Ethereum. In Ethereum, a transaction always involves at least two accounts, right? Alice sends something to Bob, 5 Ether, so Alice's account is being changed and Bob's account is being changed, and then they just redact the balance. that there are more complex transactions, but it involves always two accounts. And accounts in Maiden, they maintain state and expose interface methods, as I said. And these nodes that they can send to each other, they carry assets and have the spend script. So in a first transaction, two transactions are needed to send an asset from one account to another. In a first transaction, account 1 creates a node carrying these 5 matic in this case. And the transaction is defined as the state transition of account 1. And then there's a node with 5 matic somewhere in this UTXO tree, and account 2 at a later point in time can consume this node in a second transaction. But it's important that a transaction always involves only one account, because this is the basis for why we can create a zero-knowledge proof client-side. Because if account 1 wants to prove this state transition or this transaction, he might not have access to the state of account 2 or might not have access to other accounts, but he always knows his own state. And that's why he has everything to create this stack proof. And yeah, this is how a transaction looks like. So it always involves only one account that is defined as the state transition of this account. It can be, it can consume 0 or more nodes, and it can produce like 0 or more nodes. So basically, in theory, you could, in one transaction, send out 1,000 NFTs to different people, or I don't know, like you pay your employees in a single transaction. Or you can, like if you're on the receiving side, you can also wait until everyone has paid you, and in one single transaction you can consume all the nodes that are there for you in the node database, basically. And the thing is, there's always a proof for every transaction. And because the transaction is being executed in our virtual machine, so we have a zero-knowledge virtual machine, meaning that in this virtual machine you can execute arbitrary programs, but you will always get a proof out for the correct execution of this program. And one of these programs is the transaction kernel, so I load the transaction kernel into the Maiden VM together with the state that I know, and then I get a proof of a correct state transition out of this transaction. And the cool thing is, people can do that in parallel. I can do that at the same time as you can do that, and the network only needs to verify these proofs then, so we can have parallel transaction execution, even though like there are these synchronization points where the operators need to verify. But this is super fast. This is one of the magic things of zero-knowledge proofs, right? So proof generation might take time, but proof verification is actually quite fast. In our case, we check polynomials when we use stars, and yeah, this is quite fast actually. There are local and network transactions, and the transaction looks like on Ethereum from the process. So you prepare the transaction and say what you want to do. You sign the transaction maybe. You execute it. Execution defined as like applying it to state. So you change some data, and then you prove it. And at the end you get a transaction proof out of it. And it, like you can make it such that the network creates the proof and executes it. For example, if you have a weak mobile phone or so where you cannot run the Maiden VM in an efficient way. But the main use case is where users do the whole process, and then they just send the proof to the network. So you can think of accounts like they represent users in Maiden, and every account in Maiden is its own rollup or its own validium, basically. So you have a network of rollups.
So only the proof goes on the transaction.
Exactly, like normally, like in the local transaction case, the proof would go to the network, and then you have this, like with stacks, it's easy or easier that you have this recursive verification thing. So again, in the Maiden VM, you can also run the verifier. So when you verify a proof inside the VM, you get another proof that says you have verified a proof correctly. And so the network can basically batch proofs together, so you can verify 4 proofs together in the VM, and then you get one single proof out that you will have verified 4 proofs, and you can do that multiple times in parallel on multiple machines, and then so you can batch these proofs together and have one single proof at the end. And yeah, like what do we mean with privacy? Basically, is we will get gradually to privacy because it's a complex topic. Like we believe privacy, or that we know privacy is a human right, and it's a practical necessity for scaling. However, we also know that privacy is quite a complex topic, regulatory-wise, and there's also like the right of the society, I would say, to fight against tax evasion or whatever. But so you have to somehow balance these rights, and so we see that there are different levels of privacy. And in level 0, as like I would say public blockchain works, like everybody sees everything. Even if you have pseudonymity in blockchains like Ethereum, like even years after you've used it, somehow someone could link your account ID or your public key to your name. Whereas in Web 2, I would argue that you have more privacy, like in PayPal or even with your credit card. It's like not only the transaction participants know your identity or the address, but also the operators. So probably every employee of PayPal can see what you have done, or most of them. And then there's strong privacy, where only the transaction participants they can see everything. And absolute privacy would be that everyone only sees your data. And in Maiden, in theory, it's possible that not even the receiver knows who the sender was. If you don't want to. But yeah, we will apply different stages to privacy when the regulatory environment settles a bit, let's say. But yeah, like in mining you have these flexible transaction modes where you can have like on-chain data with network proofs, and that would be just simple transactions like you have them in Ethereum or on SDK VM. You could have off-chain data, so the data is on my computer, but I still send a network proof, so it would be a stateless transaction. I send the transaction data to a network, and then they apply everything and prove it. You could have off-chain data and local execution. This is the private transaction. And you can have local transactions where, for example, if you have on-chain data, like public shared state, everyone needs to know it, but you want to save lots of fees, so you have a very complex program. On mine, there's no limit on the complexity of a program, basically. So I could have the state public, but maybe it's a very complex program to run, and then I could do it locally on my super machine, and then I just change the state in that way that I send the proof again, and the local public state would change. Yeah, like. This is how we plan our roadmap. So next year we will be on mainnet. You can use it today. We had a different approach in Aztec. I would say Aztec started with Noir without the blockchain, and we already have a blockchain, but no cool programming language. So at the moment, we have our first version of the Rust compiler. In the future, you will be able to use Rust to write smart contracts in Maiden. At the moment it's a bit tedious for the reason because we have this zero-knowledge virtual machine that we have built from ground up that is built for blockchain usage basically, and so we need to know the instruction set, or we need to build the instruction set itself, and that means we have our own assembly language that you need to use today, but hopefully in 3 months you will be able to use the first version of the Rust compiler. And yeah, then with hardware acceleration, we have the common hardware acceleration already, but we work together with Fabric, and they built a so-called vGPU, or like a chip for us, and then we should get to 10,000 or more TPS on Maiden. Because yeah, so this is at least the goal. Yeah, that's it actually, but I'm open for questions. I have way more slides. Yeah.
So in the model where I understood where you have sends, then users can do those in parallel, they can prove them. But if multiple users want to interact, for example, with the DEX, then this is problematic, right? Because if they want to do it in parallel, then what gets applied first? Like one side of the pool will be larger or something. So
yes, I have a slide for that.
Perfect.
1 second. It's a different thing. Yeah, okay, I cannot show it now, it's in a different presentation. But basically, yeah, like there is public shared state, so meaning that 10 users could create their own node with an order to a DEX. And then the DEX would need in one transaction consume all these nodes, and in doing so would sequence these transactions. And then you would, then it would be pretty similar to how it works on Ethereum. So,
is this the DEX? Are the DEX transactions, are those public then, the swaps that happen on the DEX?
Yeah, that depends, but yeah, I would say like on the DEX, if you have a normal DEX, then these would be public, but the user still can hide where the node comes from. So the user creates a node with an order to the DEX, and this can be private, so you can use a relay account or so, and then the DEX transaction consuming these nodes and producing the swap nodes basically would go back. These would be public, but then no one would know who consumes it. Yeah, and in the same, like I don't know if you know how Zcash works, but you have this UTXO notifier thing, exactly, and then you can basically hide who interacts with these.
We have enough time for one more question, maybe.
Okay.
How does the virtual machine understand that transaction is valid? If this transaction is not transparent, so how can virtual machine validate this transaction?
Yes, excellent question. So your own computer who creates this transaction, you know that it's valid because you have the state. And then you send a proof to the network, and in the same way as Ethereum knows that the state transition of a zero-knowledge rollup is correct, right? The same way knows the mine operator that a change to this account is correct. So all the mine operator has this account database, right? And
so the miner operator can see a mine down?
No. All, like in private transactions, all the mine operator knows is a commitment to your account, right? So it knows the hash of something, but doesn't know what's behind it. And then you basically in your transaction tell the mine operator that this hash now changed to 0x and 111, and you send a proof that this is correct. And the mine operator doesn't know what's behind it, but it knows that it is correct. Because, okay, so you ask why are you not doing for us?
I understand like the logic, what you are trying to explain.
But it is the same reason, like Ethereum also knows from every zero-knowledge rollup, this is all that Ethereum knows, like it knows the state root. And like in some transactions the core data, but it doesn't really use that. And then this changes to another commitment, and Ethereum can verify the proof. And why does it work? Like in a very short version is that it is because you execute the state transition locally, right, in the mine virtual machine, and in doing so you create a very long polynomial. So basically you can think of the virtual machine as a matrix, like with columns and rows, and for every step you have like a polynomial constraint. Like for every step, you add some new small polynomial to that polynomial that it grows bigger, and then basically you encode the execution into polynomials, and the verifier can then check is this polynomial correct. But this is exactly how zero-knowledge proof works. Exactly, like you only know the inputs, like the input is this hash, and then you know it is correct without knowing what's inside. This is how, yeah. But like there is a very, very cool, if you're interested in that, like Stark 101 from Starkware, they explain very good. And Stark by hand from Risk Zero, it takes 2-3 days to do the tutorial, but with Excel sheets you then understand how zero-knowledge proof works.
Okay, thanks very much for the presentation and for the answer.
Thank you very much. That's all the time we have, but